We'll introduce you.
Great.
Hi, everyone. Welcome to our seminar series. Today, we're happy to invite Brian Gross, who's going to talk to us a little bit about the model development priorities at EMC. So really quickly, these seminars are recorded and will be posted on our YouTube channel after probably after a couple of days. Okay, so I'm going to hand it off to Ralph, who will introduce our speaker.
I'll be real brief, Brian. So yeah, well, welcome, Brian. He's the director at EMC. Been there since 2018. Is that correct? But has had a lot of other positions at NOAA. Also, you were deputy director at GFDL for a period, and got your PhD at University of Colorado, right? And so. All right. Yeah, you got an interesting coach there. Yeah, so I'm sure most of you are familiar with EMC, but I mean, if you follow the weather and you watch the news and they talk about the NAM model or the GFS model, that's Brian in charge of those amongst some other models. So anyway, turn off to Brian. This should be a really interesting talk. Yeah.
Thank you very much. So thanks everybody for attending, either virtually or online. I'm really happy to be here. One thing that I did not include in my bio sketch was the fact that I am in fact an alumni of the University of Maryland. 1983, physics and astronomy, and I also marched in the Mighty Sound of Maryland. And fun fact, my nephew is now marching in the Mighty Sound of Maryland, so we have season tickets. I'm going to forget about that Illinois game. Okay, so there is a lot of material to cover. I'm going to try and be clear and concise. I may end up having to skip some stuff, but I'm going to try and give you a picture of where we're going in model development over at the Environmental Modeling Center, just across the street if you want to visit. I really wanted to, first of all, acknowledge all of the really brilliant people that are doing their real work over at EMC. Scientists, developers, software engineers. It's just really an incredible group of people over there. And I want to also thank all of the collaborators. That includes other parts of NOAA, other federal agencies, folks in academia, such as yourselves, even folks from the private sector helping out in our model development mission. And it is truly a large collaborative and therefore complicated effort. So I think you'll see some of that complexity as we move forward. And I've linked in a link to our 5-year implementation plan, covers 2023 through 2027. And that gives you a lot more detail. It is a document of hyperlinks unto itself that links to each of the individual modeling system development plans. So if you really want to dig into the details, I hope you can go there. All right, first, definition. So when I talk about a modeling system or a modeling application, what do I mean? It is truly the soup to nuts definition of application. It starts with having a set of observations that we end up having to pre-process, and then we use modeling and data assimilation algorithms to create an initial condition. We use the model to predict. We do some post-processing product generation, and the products are generally what we disseminate as numerical guidance to the forecast community. And it's really the forecast community is making forecasts. EMC doesn't make forecasts. We make the forecasts better, so to speak, to steal from the BASF commercial. And I think most of you, I think, are familiar with the multiple or individual pieces of this. But the important thing for me is that, first of all, the processes that are involved in stitching all of these steps together, all the way from observation ingest out to product dissemination, requires a workflow. It can be extraordinarily complex, and it can be extraordinarily personal. So that sometimes it's a little challenging to develop a uniform workflow across applications from user to user, and so forth. And then finally, we want all of this is being done in something that we're still trying to build here, a collaborative environment for the development of operational numerical weather prediction applications. So what applications do we have? There's a few. as you can see in this picture on the left-hand side of this slide, there are well over 20 individual full modeling applications that are currently being run operationally. There are a lot of dependencies between those applications, and it makes what we, I think, fondly call the quilt. This is what we call our application quilt. It makes it pretty complex. Particularly when the core of the system are the global systems, and they drive a lot of the, say, regional prediction systems, the hurricane prediction systems, and so forth. Changes in the global system can percolate down to changes in some of the downstream systems. And so we have to be very careful about changing some of these systems because they do impact other systems. So this is really, really hard to maintain. There's a lot of applications. The implementation process is pretty strong because we need to be able to make sure that the models run operationally on time all the time. And I think this quilt of applications has grown cumbersome enough that we need to try something different at the Environmental Modeling Center. And so the simplification of this NCEP production suite is really what is framing our progress here. So where do we want to go? First of all, we want to cut down on the sheer number of applications because each one of those, even if they do similar things, requires an implementation process that can last up to 2 years. That's a long time, right? It makes getting innovation into the operational systems hard. So let's simplify it. And we're going to simplify it along lead times. So we have analyses, right? Zero lead time, if you will. We have an application called Warn on Forecast, which is really issuing things like tornado warnings, severe thunderstorm warnings, based on what the model tells you, not waiting to see whether you actually observe it on the radar from some other observing systems. We have the shorter range, say, convective scale regional modeling systems. We have the global systems with lead times out to a week, maybe a couple of weeks. And then we begin getting into the longer scale systems, the subseasonal systems. We use a global ensemble for that. You might know it as the Global Ensemble Forecast System, or the GEFS. And then we have an even longer lead time application. Right now, it's the Climate Forecast System for seasonal prediction, right? And excuse me, the Climate Forecast System is one of multiple seasonal prediction systems that are combined into what the Climate Prediction Center creates, the multi-model ensemble, which includes multiple, excuse me, climate prediction systems. And so what we've settled on are a smaller, much smaller set of applications, basically in the weather space, one for each lead time, as well as some specialized applications for particular phenomena like air quality, like hurricanes, like space weather, things like that. Okay. So really honing down the number of modeling systems that'll make it much easier to develop, upgrade, and implement these new systems. How are they built? Well, first, let's start with the outside. So these are these new applications. They are based on the Unified Forecast System. The Unified Forecast System, or UFS, is really a set of shared and common components. It can be an atmospheric diacore with a set of physics options coupled to an ocean model and a sea ice model with an independent land model. It's surrounded by a common data assimilation system. It is accompanied by a set of reforecasts and hopefully a reanalysis, if we can afford it, to help with model calibration. And so out of this common set of components that you see here are built each of these separate applications. So space weather will require a deep atmosphere coupled to an ionosphere plasmasphere model, right? That is the space weather prediction model that they're creating out at the Space Weather Prediction Center in Boulder in collaboration with EMC. And more familiar applications like the GFS, the Global Forecast System, and a hurricane application. Again, all using a common diacore. We're centered on the FV3 diacore right now, trying to integrate through a common community physics package for the atmospheric physics. Waves, we're using WaveWatch 3. We have a number of options for the land model. We're focusing on Department of Energy's sea ice CICE, depends on how you say it. And so through this common set of components, we're building these applications. Again, it's a simpler approach than just sort of accreting additional independent modeling systems based on the phenomena. There's a lot of shared infrastructure. We share it within EMC and with our development partners throughout the community. And this includes the coupling, the way that we do coupling, the software engineering for coupling. And that is based on ESMF and some higher level uses of the ESMF subroutines. Interoperable physics, I already mentioned the Common Community Physics Package. Workflow, community-friendly workflow, I said earlier, is a challenge, and it's still a challenge, right? Centering on a way to process across applications, even across partners is sometimes a challenge. Hierarchical model development. So suppose you have the next best thing in microphysics. Suppose you can't afford to run the full model. So how do we integrate your ideas into the big operational model? We can do it through a set of hierarchical testing frameworks, like a single column model to start with. And then we can do a low resolution simulation. And then we can finally get to the operational application. So it's this hierarchy that lets us get this stuff in. Verifying the systems is essential, right? It is not modeling per se, but it's making sure that those models are doing what we think we're doing. It is all based on the MET+ package. MET+ is very comprehensive, and with that comprehensiveness can come complexity, but we need that comprehensiveness in order to verify across all the applications that we're building here. Repository management tools. All of these applications are open development, right? It's not just open source where you can get the code. It's open development where you can get the code, innovate, and contribute that code back. So that requires repository management. We're all using GitHub and the set of tools that reside there. And then finally, the support, right? We have something called the Earth Prediction Innovation Center, EPIC, in NOAA, that is going to marry those of you that want to help develop UFS applications to the actual technical development itself. So how do we get from that quilt when all the current applications to something that's simpler? All right. This is a notional way of doing it, and it's sort of organized in the following way. On the left-hand side here are all of our current applications, right? Roughly, the global systems are up here at the top, and they're all converging into the green here. The limited area models, the mesoscale systems, the NAM, the RAP, the HER, and so forth, they're the bluish colors, and they are all going to coalesce into a rapid refresh forecast system, which I'll talk more about later. We have the hurricane prediction system and other application-specific modeling systems. Again, there's one for air quality that will eventually be merged into the regional system. At least that's the plan. We've got waves on the Great Lakes. We've got space weather, and we've got evaluation systems. So the idea is to look at where we are now, march forward in time, and eventually, piece by piece, begin combining these applications, really developing these new applications and sunsetting the legacy applications to get a much simpler production suite here on the right-hand side. Fewer, granted, more comprehensive and complex applications, but fewer. So the implementation cycle, you don't need to implement quite as many systems into operations. So the UFS community, there's EMC. We're kind of at the, I'll describe this so-called R to O funnel. So those of you that are familiar with technical readiness levels or just readiness levels, basically you've got basic research up here at the top. And down at the very bottom, you got operations. And there is a transition process as you go through the development of proof of concept, and then you go into prototypes, and then you go into operational prototypes, until eventually you end up developing an operational application itself. So EMC's bread and butter is that sitting right here, at the very bottom, to make sure that all of the innovation that's taking place in the research and development world are making its way to NCEP central operations. They actually run the systems on the supercomputers. And that is our fundamental job right now. So what happens when you open up development to the community? Well, it becomes more complicated. Life does become much more complicated at EMC because we get to talk to a lot more people, and that's a good thing. So we've got the community out there. I already mentioned the academic community, other federal agencies, the private sector that we can talk to about what do the operational applications need. My boundary layer is giving me terrible convective available potential energy. So how do I fix that? Challenge the research and development community with those operational problems. Take the innovations that they have, put them in at the appropriate spot in the funnel, whether it's a brand new idea that's never been tested, whether somebody has access to the operational systems and can test them in the full operational framework. The idea is to help them get their innovations in. And EMC, because we are the penultimate step to operations, we want to be involved as high up in the funnel as makes sense, right? We don't want to do fundamental research at EMC, right? We don't even want to necessarily step on the toes of our sister laboratories over in OAR, another line office within NOAA, but we do want to join with them at the right time to nurture their innovations into an operational framework as soon as possible, so that we're not just sort of handed something and expected to implement it operationally. So it's really being involved across these steps, managing code, nurturing innovation, nurturing it through the funnel, doing the penultimate development in order to get into operations. That's what EMC is doing, okay, in the UFS. And the UFS is comprised of within NOAA. There are a couple line offices that actually fund the UFS, but they fund outside of NOAA as well. So it is truly a community effort. The focus recently has been on something called the R2O project. And if you look at this entire milieu and you look at the funnel, the R2O project kind of sits down here. The R2O project was founded to try and get some of these innovations into operations, right? That's where NOAA's focus is right now, and it has been over the last 3 years or so. And there are really 3 big application areas that the R2O project has attended to. Medium range weather out to subseasonal and seasonal scales. These are the global systems. Short range weather, really the limited area systems, and then the hurricane system. So I'm going to go through each of these, kind of tell you where we are and where we're going. Let's start with hurricane analysis and prediction system. It's called the HAFS, right? V1 was implemented operationally in June. It has improved. So here on the right-hand side, the track skill, anything above the 0 line means HAFS is better than its predecessors. So across the board, HAFS is better at track forecasts than its predecessors, at least in this sample of forecasts. And down below in the green is intensity. Picture's not quite as clear with intensity. In fact, HAFS actually does worse at 3-day lead times than its predecessors. So what happens with that? Well, there's some good things in intensity prediction, particularly at the shorter lead times here, but we still have work to do for HAVS. So that's why it's HAVS V1, and we plan on attending and developing HAVS for HAVS V2, which I hope we can implement next summer, right? HAVS is structured as a limited area grid within which moving mesh is embedded, and that mesh covers each individual storm. Right now, there's a number of different domains in the coupled system. So HICOM is in this orange domain, the wave domain is in blue, and the storm nest is in red, and we can do it for a storm at a time. The goal here is really to grow the system so that it is basin scale and eventually global scale, where we will have a global system within which is embedded multiple moving meshes, one for each storm. Right? We know based on the last few years of activity, that's a capability that we need to get. So that's where we're going with that. Want to move on to the global systems. So all of the global systems, we really want to build fully coupled systems, both for the global forecast system, the deterministic, the ensemble forecast system, which goes out subseasonal scales, and the seasonal forecast system. Fully coupled, 6-way, eventually growing to full Earth system capability. So 6-way, atmosphere, ocean, land, sea ice, waves, and atmospheric aerosols. So addressing the air quality problem, right? We'll eventually want to get into things like ocean biogeochemistry, right? Land ecology, ecosystems, agriculture interests that want to know what the seasonal prediction, what the seasonal forecast is going to be for the growing season. When should they plant? How much rain can they expect? What is the impact on the atmosphere of what they plant? So I came to find out when I got to EMC that cornfields, amazingly, actually have an impact on the boundary layer profile based on their evapotranspirative properties. This is what I mean. It's besides it being incredibly fascinating stuff, you got to be able to handle that kind of thing. Okay, so that's where we're going across the spectrum. This animation that you're seeing right now is really a HERO integration. It is a 3-kilometer atmospheric resolution coupled to an ocean system with sea ice and a land surface. NOAA is our target. I don't think we're using NOAA here, but you can see it's got realistic synoptic systems. Every now and then you see a hurricane. So we know we can do it in some structurally zeroth order way. I have no idea what the skill of this system is, and it's too expensive to run to actually find out, but it is a target, right? It's a target for the future. So we developed a number of prototypes of these coupled systems, and this is really just a depiction of progress that we've made. So for example, in the dynamical model, we've moved from 64 vertical levels to 127. So we're increasing the vertical resolution. We're also increasing the depth of the atmosphere that the system covers. In terms of the land model, we're moving from the NOAA land surface model to a NOAA MP land surface model in collaboration with the folks at NCAR. In terms of the modeling infrastructure, our mediator is moving from the NOAA environmental modeling system over to the CMEPS, which again is out of the ESMF group in Boulder. And each of these things, the wave model, we didn't even have a wave model in the early prototypes. We're now coupled to WaveWatch 3, different versions of CICE and so forth. So it is this progression, we're moving from prototype to prototype, and that progression has allowed us to improve bit by bit the pieces, the skill of the forecast in using these particular metrics. So one metric that we're using to evaluate these systems is the MJO. You can see on the left-hand side, I'm just going to focus on the RM1 plus RM2 figure. Our current operational seasonal prediction system is depicted by this gray dotted line, right? This is the skill that we have in the climate forecast system, and these and skill being okay. Where do you hit 0.6? The notional idea when you're skillful. And the black, red, and green curves are prototypes 6, 7, and 8, the last 3 prototypes that we developed. And you can see a gradually increasing length of skill. So we went from CFS, which has skillful lead times of about 12 days, out to now 21 days. Adding days to your skill is incredible. And these are prototypes, right? This is not the finished system yet. So we're very, very encouraged in where we're heading in this direction. We still have some work to go. So I'm going to talk, the next few slides are going to talk about 2 different things. One is the development of GFS V17, which is our deterministic prediction system. Slide after that's going to talk about the global ensemble forecast system, right? So for the deterministic system, which typically, if you watch the evening news, you will often see the American model, or as Ralph said, right? GFS, they'll actually mention that. Where are we going with that? So it's not coupled right now in operations. It will be in GFS V17, the next operational version. Our DA is based right now on GSI, and we're going to move to the JEDI framework, and I'll talk a little bit more about that later. We're incorporating into the new NOAA MP land model, Thomson microphysics, and other physics upgrades. We're going to be using the unstructured wave grid for WaveWatch 3 with 2-way coupling. That's the plan. The development process will tell us whether or not it's A, something we can afford, and B, something that helps us with our skill. And we're moving to higher resolution. 9 kilometers is what our target is for the deterministic system. It's 13 right now. We're hoping that these and other improvements are going to help address known issues in GFS V16. I mentioned the boundary layer. It also has a cold bias, and you might have heard about a hot bias in the warm season. in GFS. We think that has something to do with the way that with soil moisture deserves exploration. We think with new NOAA, potentially some new microphysics, we'll be able to make some progress on that. And again, in terms of getting rid of legacy applications, so we're going to combine the ocean data assimilation system, GODAS, in with the GFS data assimilation system, the global data assimilation system, just GDAS. And we're hoping to retire some of these legacy systems like the NAM. The NAM is a limited area model at 13 kilometers. GFS right now is a global system at 13 kilometers, but it has boundary layer characteristics that the forecast community, I'll say at times, doesn't appreciate as much as it appreciates the boundary layer characteristics of the NAM or the RAP. So we keep running these things. We'd like to be able to sunset those, but it'll depend on how good the next version of GFS is in the areas of interest. When it comes to the ensemble forecast system, right, we're really hoping to have the same model configuration as GFS. And when I say that, I mean the latest components are going to be shared between the deterministic system and the ensemble forecast system. We're not going to be able to run a 9-kilometer ensemble. Some people can afford to run that, right? ECMWF is running a 9-kilometer ensemble, 51 members. We cannot, we don't have the computational power to run that, along with all of the other applications we need to run, like the hurricane prediction system, like the limited area systems. We're going to include interactive aerosols. These aerosols are, for the first time, going to be radiatively active. Right now, they're effectively passive tracers. We'll make some upgrades to how the ensembles are initialized. We'll make some upgrades to the model physics, in particular, introducing stochastic methods to try and increase model spread. The big kahuna when it comes to these systems is a reanalysis, reforecast. I mentioned these earlier as a way to calibrate. It also is something that we want to use to train machine learning algorithms on our system. These are extraordinarily expensive things to run. They can take up to a year to finish, right, from start to finish. So we have to plan for that big chunk of time. It's one of the reasons that once we freeze the code, it can take a long time to get into implementations. Again, improving on issues with the current operational system, GEFS v12, and we're hoping to retire the short range ensemble forecast system, the SHREF, when we implement GEFS v13. Again, we're here to serve the forecast community, and they'll have a big voice in determining whether or not we're going to be able to accomplish the retirement of some of the legacy systems. And then finally, I want to get to the new seasonal forecast system. So last fiscal year, our fiscal years are October through September, in case you didn't know. We received additional funding to develop an operational seasonal forecast system to replace the climate forecast system, which at this point is, I think, pushing a dozen years old, right? It hasn't been upgraded in a dozen years. It's really showing its age, as we saw earlier in the MJO statistics. So there's a lot that goes into developing a seasonal forecast system. One of the most important things is design, okay? What is it going to look like? A lot of that is going to depend on what we can afford to run, right? These are 9-month to 1-year integrations. They are expensive. If we can't afford 9 kilometers in the GEFS, I can guarantee you we can't afford 9 kilometers in the seasonal forecast system. So we have to make some trade-offs there. Ensemble size, resolution, model complexity. These are all trade-offs that we can make to make these systems more affordable. So we have an entire plan for developing. We're just getting going. Okay, so stay tuned. We're encouraged by the results that we see in our coupled prototypes that we're going to get some quick wins with the SFS. All right. For example, our coupled prototype is showing a single ITCZ. We don't have a double ITCZ, right? I saw this graph, I think maybe a week ago for the first time, and I couldn't believe it, right? Now, are we getting the right answer for the right reason? That's what development's all about, is trying to figure that out. But again, this is from an early prototype, right? Yeah, it's P8, but it's still a prototype. We're very encouraged at this kind of progress. Still some issues, right? It's a little too intense, but the structure seems to be there. Okay, again, very encouraging. So I want to move from the global to the regional systems. This was the real driver for us moving from sort of that quilt into a simpler production suite. We had multiple regional systems that I'll say for me coming to EMC in 2018 looks to me like it was by accretion. Somebody had a requirement, they built a prediction system to meet that requirement, put it into operations, and it just kind of grew. We're going to try and re-baseline how we're managing our regional prediction system. So we're building something called the Rapid Refresh Forecast System. It's supposed to take over the responsibilities of the NAM, the RAP-HER, and the high-res windows, right? All of those are legacy systems that we're hoping to sunset when we implement the Rapid Refresh Forecast System, right? It is a limited area model, again, based on the common FE3 dynamical core built at GFDL. It is updated hourly with 3-kilometer grid spacing, 35 layers, uses hybrid 3D and VAR assimilation with 30 members, has smoke and dust capabilities, deterministic forecast to at least 18 hours every hour, and ensemble forecasts out to 48 hours. This is also new. One of the things that we're trying to figure out is these are the kind of details that we need to worry about in operations, right? NAM goes out to 84 hours. We don't have a limited area model that goes out to 84 hours now. So that's a challenge that we're going to have to figure out if we're actually going to sunset the NAM. So we take all of these various domains, the NAM in black here and the nests in colors, the RAP-HER subdomains, one for Alaska, one for CONUS, and so forth, and combine them into this single red domain here. It covers all the U.S. interests, right? The CONUS, continental U.S., Alaska, Hawaii, Puerto Rico, and we'll talk a little bit about how we can improve even on that. But this will be the first limited area system that covers all those geographic areas in a single domain. So implementation here, going to be a couple of years. This is a beast. It's big, got a big domain. It's got high resolution. It's expensive to run. So the pace of development is challenging. But the good news is we've got a lot of very smart people at EMC and within our collaborative community to try and get us there. So think maybe in a couple of years or so, we'll get to an operational version of V1. So this is the entire domain depicted here on the left-hand side. It is at 3-kilometer resolution. And what that does is it lets us, telescope in to see what the heck's going on at these various scales. And you can see there's an awful lot of structure in that huge domain with these convective systems. And we'll have a few more words to say about the convective systems. But for the forecast community to be able to look at a single domain, anywhere in that single domain, to see features of this resolution is really a big win. For documentation purposes, I'm not going to go through all of this, but these are the physics packages that we're using in the RFS, and this is a depiction of how the vertical levels are distributed. So if you're really interested in the details, go back and check these things out. We've seen some good things with the early versions of the RFS, and these are things that we're intending to keep. So if we look at the vertical profiles averaged appropriately in temperature, so the operational HER, high resolution rapid refresh forecast system, is in red, and the RFS under development is in blue. So this is these are biases. You can see the biases in dotted lines. We've got some generally in mid and upper levels. The RFS has, sorry, I got that backwards. We've got, oh gosh, I knew this would happen. Oh, I know why, because I changed the slide. Never changed slides this late. All right, I'm gonna start on the right-hand side in the winter. So this is cold season stuff. Again, HER is in red, bias is dotted, and the root mean square errors are in solid. So you can see RFS here is slightly reducing the root mean square errors, and it's significantly reducing the biases in the cold season, except maybe for a little bit here at the boundary layer. The boundary layer has tended to be one of our sore spots at EMC. Then if you go to warm season, then the problems become a little bit more apparent, where you can see that the bias in temperature for the RFS is actually, at or larger than the bias for the HUR at mid or upper levels, and significantly colder in terms of bias than the operational HUR is. So again, that is a developmental challenge, right? Picture's not quite as bad when it comes to root mean square error, but still, I mean, the red curve is to the left of the blue curve, pretty much throughout the column. The RMSEs for the HUR are better than for RFS. So again, these are the developmental challenges that we face in getting the RFS up to snuff for operations. One of the other issues with the RFS that we've seen is that it has a wet bias. And one of the reasons it has a wet bias is that it creates a lot of almost grid point scale, so-called popcorn convection. So in this picture on the left, the upper left is just basically observations. I think that says MRMS up there. And these are 3 different variants of an FE3 based RFS. And you can see the very small scale intense convection to the point where effectively all the water in the column rains out, right? Rain rates of up to 3 inches an hour in some of these things. So this is an issue that we need to deal with in the RFS. And we're doing so by looking at improved radar data assimilation. We know one of the problems is the way that the RFS is initialized, particularly when using radar data, and looking at parameterized scale-aware deep convection to try and tamp some of this stuff down. So we have our work cut out for us on the regional system. Lots to do. We also have to figure out how we're going to build an ensemble-based regional system. We'd like to do it with a single physics package, but that might not give us the spread. So we may need to use multi-physics options. So, and again, making sure that your spread is appropriate for an ensemble is really, really important, because there is nothing more detrimental to your ensemble system than having a very, very confident and wrong forecast. Right? And one of the issues that we're going to need to deal with is expense. Instead of running all the ensemble members starting at the same time, we will probably stagger them. This is how we're I think this is what we're doing with the climate forecast system right now. So, we'll start some of the ensemble members and then overlap start with some of the others, so it becomes less of a computational burden overall. So all of that is for the initial implementation of RFS. What are we thinking about even beyond the next implementation of RFS? So this is the N+2 almost, what we have here. So one of the things that we're looking at is whether the die core, the FE3 dynamical core, is something that we might be able to switch out and use the MPAS dynamical core from NCAR. It has been demonstrated in some early simulations that MPAS has some superior depictions of convection. And that is what is leading the community, along with the EMC, to consider an alternative die core to what we have. Now, the downside of this is it actually breaks some of the simplicity that we have in the production suite. You're adding a different die core in, and all the other systems are using FE3 except for the RFS. So it's additional complexity, but in the end, if we're going to serve the forecast community, the superior numerical guidance, this is something that we need to consider. We'd like to add into the big domain support for American Samoa and Micronesia. These are all U.S. interests that are part of the Pacific region in the National Weather Service. Trying to get the ensemble right. Can we get to single physics? Don't know yet. I'll talk more about this transition to JEDI in a bit. And then there's a variety of other things that we're trying, that we're thinking about for RFS v2. Remember, RFS v1 is probably a couple of years from implementation. RFS v2 is the one after that. So in summary, they're really trying to consolidate the current suite of operational systems under a single regional system. Hopefully, we'll be able to freeze the science in about 6 months or so. Implementation, maybe up to a year after that. So get RFS v1 into operations, and then move on to RFS v2. Air quality. I don't know if it's common knowledge, but it's common knowledge for me. The mortality from air quality far exceeds any other weather-related phenomena. I mean, like far, if you look at it on a linear scale, there's nothing else except for air quality problems. Okay. If you look at it on a log scale, it becomes a little bit, a little more comparative. So the Weather Service doesn't have a mission of providing air quality guidance per se. We provide forecasts, I should say. We provide our numerical guidance to EPA, the regional state folks, to let them issue air quality forecasts. So nevertheless, the guidance needs to be solid for those customers, even if they're outside the Weather Service. So what we're doing, we're taking an approach similar to what we're using for the hurricane system. We have a large domain that covers CONUS, Alaska, and Hawaii. We actually have a parallel that's been running over a year now in this large domain. It's not it's not high resolution, right? It's 13 kilometers, much like the global forecast system is right now. But it is running in real time, and we're hoping to implement it in early 2024. We're happy with the results that we're seeing so far. It's able to capture a lot of the air quality issues associated with wildfires in the Pacific Northwest in this particular simulation. And so as we, again, continue to evaluate the system, we'll be able to watch this kind of stuff. And the improvements to the air quality model, I think we're at version 7 right now, is the one that we're going to implement. There's still a question of whether we can integrate this aerosol capability into the regional system, the RFS. It might be too expensive. Remember, this is a limited, whoops, maybe I'll try that. Yes, so this is a limited domain, but it's at relatively low resolution compared to the RFS itself. So trying to integrate into the RFS might be a little too expensive, but nevertheless, it's an important problem, right? By the way, if you go back and look at these slides, so the dots are stations, right? So they take their measurements, and the simulation are in the shaded regions, and you can see the correspondence between the wildfire emissions that are observed and those that are produced by the models, and then even some of the later intrusions that wander into the U.S. are captured in the observations and the model. Okay, let's talk about data simulation. The grid point statistical interpolation, GSI, has been a mainstay at EMC for many, many years. So the Joint Center for Satellite Data Simulation, which is supported by multiple federal agencies, NASA, NOAA, Navy, Air Force, as well as some other partners, are developing the Joint Effort for Data Simulation Integration, or JEDI. They have a proclivity for Star Wars-based acronyms, in case you don't know. And this is a software infrastructure that is going to abstract out a lot of the work when it comes to data simulation. So it's model agnostic, it's generic, it is portable, it is open source. It doesn't impose an algorithm, but it lets you use different data simulation algorithms like 3D VAR, 4D VAR, et cetera. And it'll allow us to coalesce around a single software infrastructure for data assimilation. Okay. How are we going to use it in our future applications? So the full JEDI is not available right now. The Marine JEDI is. So we're going to plan on using Marine JEDI in the next implementation of the global systems. Then the second implementation of the regional system and the second implementation of the global system will use the full package of JEDI from the JCSDA. Okay. So for the global system, the deterministic GFS, right now, we will be able to use the JCSDA software in the marine layer, but we're going to keep GSI for the atmosphere. We'll keep GSI likely for the land piece, and then the aerosol piece we'll be able to use a 3D VAR out of JEDI. Again, these are the plans for GFS V17. We've seen actually from the Marine JEDI pieces, we've seen a lot of success. Okay, if you look at the This is background minus obs. So the GFS, the red curve, is where we are right now. If you look at just a data atmosphere, right? So you have a evolving ocean, use data atmosphere, and you use the assimilation software from the JCSDA, you go from the red to the blue curve, right? Now, if you combine GSI with an active atmosphere, not a data atmosphere, but the real in quotes atmosphere, combined to these other marine components, and you use the JEDI software, you get down to the orange curve, and then you can refine that even further. So you can see the error, or the difference, I should say, between the background and the observations has really been pounded down quite a bit by the use of this software. And you can see that on the right-hand side by smaller O minus B increments almost everywhere in the field by using the GSI plus the marine JEDI pieces. You can also see this in some of the sea ice simulations where we've been able to significantly reduce the error in a weakly coupled data simulation sense in the sea ice with just a data set, data atmosphere, and the JEDI software. We can get this lower left-hand figure. If we use weakly coupled data assimilation with GSI in the atmosphere, we can get something that's much closer to the sea ice observations in this figure. And the data assimilation milieu, if you will, at EMC is summarized in a couple of documents. There's a history and a current status document that I think will be available hopefully soon. There's also a 10-year strategy for EMC's data assimilation plans. And this 10-year strategy is actually a huge component, probably the biggest component of NOAA's overall data assimilation strategy, which is something that's also in development. All right, so everybody's favorite topic these days, it seems, is artificial intelligence and machine learning. So interestingly, EMC's had a very, very long history in looking at the application of these kinds of techniques to the weather prediction problem, all the way back to 1995. And of course, others are looking at these things too. But the rapidity with which attention on AI/ML techniques in numerical weather prediction has grown has been phenomenal over the last few years. So right now, these are the different areas in which EMC has interests in developing machine learning algorithms, all the way from the observations and their processing to the DA, the forecast piece, and the post-product. So all of those pieces of the applications that we're talking about, we have interests in. NOAA is hosting a machine learning in numerical weather prediction internal meeting to basically get our act together as much as possible. I think EMC, I know, is pretty far behind some of the other centers in poking around in the AI/ML space, particularly when it comes to applying surrogate models, right? The one comment I'll make on that is, no, we're not going to replace our need to know how the Earth system works with AI/ML. We're always going to have to be able to train those systems on something that is beyond the reach of just, for example, current observational data sets, right? So probably if you ever talk about modeling in NOAA, you wander over next door, you're going to hear something about high performance computing. We're always short. And you know why? It's so much easier to fill up a high performance computing system. Every doubling in horizontal resolution requires almost an order of magnitude more HPC to run the forecast piece in the same amount of time. And so this is a depiction of where the current set of applications, so there's GEFS and GFS and the hurricane system. This is the piece of the operational supercomputer that they take up right now. All of the applications I've talked about previously are going to start bumping up against this black line, the limit of W cost 2. Moreover, you can see how spiky this is. So we're trying to figure out a way to use the dead space here, places like this, more effectively, right? How do we, it's a game of Tetris. How do we fill the machine most efficiently? We have a lot of supercomputing, or W cost itself is, I think, it's pushing 35 petaflops. It's a big system, but we have a big mission, right? We have global, regional, application specific, like air quality and hurt. We have a lot of different things that we need to forecast. So we need all of this space. So I'm going to wrap up and talk about sort of the big picture, right? We've talked about where we're going with some of these individual applications, reaching, years ahead of time from where we are right now. But are we even thinking broadly enough? So one of the things that I'm challenging ourselves with is reimagining what the production suite actually looks like. I think one of the things that we can do more efficiently is actually have a prediction backbone that is based on, you can call it a digital twin. That terminology makes me a little bit uncomfortable. I just think it is a constantly assimilating state estimating system that is being run all the time, right? Constantly updating the state of the Earth system. When you think about state vectors, it is updating the state vector of the Earth system. This is the backbone of any prediction system. If you have this and you have a solid training data set, you can use all sorts of ways to run the prediction itself, right? You can use surrogate models with machine learning, right? You can reduce the number of times you run the global system, right? The global system right now is run 4 times a day. What does that do? It limits the window of data that we can actually assimilate in the global system. So suppose we went to two times a day, and we can grow the window of data that we can actually use in initializing the system, right? Hourly cams, or more frequently worn on forecast systems that are very site specific to warn of severe weather, right? And other ad hoc, that is application specific, on demand prediction systems for dispersion, for hurricanes, for fire weather, right? Things like that. And because of the variety in the forecast community, you're going to want a variety of approaches. Some rely on the deterministic systems. Some rely on the ensemble-based systems. Some are more interested in going to these cheap surrogate systems that let you build a very large ensemble relatively cheaply. But as long as they have a solid foundation for training, these surrogate systems, I think we'll be in pretty good shape. So we need to build and develop these deterministic or ensemble-based systems regardless, because we're never going to get the training data set without those things. So keep the science up. And then finally, we host on-site computing systems. I think we're going to go to the cloud, if only because if we move toward a backbone capability, these on-demand prediction systems don't require a constant sitting set of nodes, right? You basically get HPC by the drink. I hope it becomes cheaper than it is right now, because right now it is cheaper to host our on-prem systems than it is to use cloud for our mission. But I expect those costs to come down, and I think we're going to end up moving at least a lot of the development into the cloud when it does come down. All right, so that's it. I left you 3 seconds for questions, so thanks.
We can have a few more seconds than 3.
Right.
So if anyone has any questions, you can go ahead and raise your hand. There are online questions, so if you're online, please type it in the chat. In person, just wave. So the online question, I think you said the intended replacement for NAM doesn't forecast out to 84 hours at this point. What is the obstacle? Do forecasts become unacceptably inaccurate before 84 hours or something else?
Yeah, sorry. So I should have been clear. So the NAM forecasts out to 84 hours, right? There's a need in the forecast community for that. That is the only regional system right now that goes out that far. So we can't just get rid of it because we'll lose guidance in a particular lead time. So we need to find a replacement for it. So I don't know if we can, the idea is to get the RFS to eventually meet those needs, but it's very, very expensive, right? We're not planning on going out to 84 hours with RFS. So there might be other options out there with some of the current legacy systems to extend those out to 84 hours. Believe me, anytime we can get rid of a legacy system, it's going to be a win for us. So that's the philosophy behind trying to sunset the NAM by finding a different application that can go out to 84 hours and meet the lead times that the NAM is currently serving.
Thank you. Any more questions?
So, Brian, that was a really interesting talk. So in the satellite world, there's a big push for the private sector, the CubeSats, the small sats. Like, how do you see that fitting into all of what you guys are doing?
We are already assimilating commercial observations from those satellite systems. A lot of them are the radio occultation observations, and we don't see that train stopping anytime soon. One of the things that we would like is help. The private sector is part of our community here, and if we can get some help in terms of characterizing errors, for example, in those observational data sets, that would accelerate our ability to ingest those kinds of operations and actually assimilate them. There's also this idea that there's a lot of redundant observations. So the more unique you can make your observation, the more impactful it will be on skill. So I think that's another important consideration for us and for the folks that are building these systems to think about. But yeah, they're there already, and we're expecting more.
Thank you. Any other questions before we wrap up? We're just about at the hour. Okay, thank you everybody for coming to this talk, and thank you to Brian Gross for giving us this great talk. We'll resume next week, same time, different place though, online.
Go Terps.
Go Terps.